All right, our topic here is inequalities. So these are going to be items that have solutions that are ranges of numbers usually. X will be greater than or less than a certain number, or maybe in between a few certain numbers. And we're going to talk about four different styles. And we're going to start with one that kind of combines two things. A linear, meaning it's just x to the first power. So we're going to solve it by trying to isolate x. And compound, this is two inequalities in one. This expression in the middle has to be in between -2 and 4, including -2 but not 4. If it's compound, normally when you do an inequality or an equation, what you do on one side you do to the other. Well, with something like this, what you do to one part you do to all three parts. So it's not a big stretch to extend it to three parts. The first thing I need to do is get rid of the divided by 3. I'm going to multiply everything by 3. And that's going to leave me with -6 on the left, 4 minus 2x in the middle, and 12 on the right. Next thing I need to do is subtract 4. What you do at one spot, you do in all three spots. So that's -10 on the left, -2x in the middle, and 12 minus 4 is 8. And the one thing about linears that's sometimes easy to forget, the key difference between solving an equation and an inequality is when you divide by a negative, you have to point your signs the other way. When I divide all these parts by -2, I get 5 is greater than or equal to x, which is greater than -4. Notice how it wouldn't make sense to point these things the other way, because if x were greater than 5, it couldn't be less than 4 at the same time. All right, this is an and situation. X is two things at once. It's greater than -4, and it's less than or equal to 5. So that would probably be okay for the answer. I would prefer it just rewritten in the opposite order, so it makes sense reading left to right. But what we have is x between -4 and +5, including +5. All right, second one is absolute value. I'm actually going to do two of these. On absolute value, greater thans are ors, and less thans are ands. Okay, absolute value is a distance. So if your distance is less than a certain amount, then you can't go any further away from that value. So this is the kind of inequality that's shaded in between. An and. It is left of one and right of one at the same time. An or is the type that ends up shaded outwards. In my very first year teaching, one of my students made this up. She said just simply gore and land, just to help her remember that greater than is or and less than is land. If that helps, use that. If not, you can remember it however you want. So we have an or going on here with the first one. If the absolute value of x minus 20 is greater than or equal to 4, a couple things could be happening. X minus 20 could be something like 4 or 5 or 6. That's greater than 4. It could also be, or it could be, on the other side, it could be less than -4, -5, -6. So I think it's best just to split this into two parts with an or in between. Either x minus 20 is greater than or equal to 4, because remember, with absolute values, if the quantity inside is positive, then the absolute values are meaningless. Or x minus 20, squeeze my or in there, is less than or equal to -4. So put an or, flip the sign to less than or equal to, and change 4 to negative. And now we just solve two separate inequalities. On this one, I'm going to add 20 to both sides. X is greater than or equal to 24. Or x is less than or equal to, and when I add 20 here, I get 16. -4 plus 20 is 16. So x can be in two places. It can either be less than or equal to 16, or greater than or equal to 24. Okay? So greater than absolute value is an or. It's outward pointing arrows. Less than is an and situation. And this one you can write as compound if you want. Let's isolate the absolute value first, just to get that annoying step out of the way. So if you divide both sides by 4, it just takes one step out. So in and, I know that this expression, 3 minus 2x, it's less than 2 and it's greater than negative 2. So I would do this. Just rewrite it as a compound inequality, the same way that we had on the first slide. If you do that, then you can just work with, it's 2 parts, but you could just work with one statement rather than 2 separate ones. I'm going to subtract 3 from both sides first, giving me negative 5 to negative 1. Divide by negative 2, that gives me 5 halves here. Again, we divided by negative, so I need to point my symbols the other way. So x is between 1 half and 5 halves. I'm going to flip it back around to put it in increasing order. And then that graph, here's 0, here's 1 half, and somewhere down here is 5 halves, shaded in between with open circles. So, long story short, land, GOR, less than is and, greater than is or, less than is shaded in between, greater than is shaded outward. All right, so polynomial inequalities. When you're solving these, it's kind of like solving polynomial equations. If they're quadratic, then we've got options. We can factor, set equal to 0, quadratic formula. If it's greater than quadratic, if it's cubic, 4th degree, 5th degree, either it has to be written specifically to factor by grouping or some other technique, or we're going to have trouble dealing with it. This one's just quadratic, so we're not going to do anything too crazy yet. This one's quadratic, which means I need to have it equal to 0. So let's start by subtracting 16 from both sides. 9 minus 16 is negative 7. Once it equals 0, I can factor as long as it will factor. Negative 7 will factor to negative 7 plus 1. Those add up to negative 6. Now, we've got some options. We've got we could do test values. We can do sign charts on a number line. But here's what I encourage you to do. This is a parabola. This parabola crosses the x-axis at 7 and negative 1. Right, because the factors are x minus 7, so one of my solutions is 7. X plus 1 has a solution of negative 1. It has a y-intercept of negative 7, but that doesn't really matter. I'm just going to kind of sketch. This is an opening upward parabola that I'm not drawing to scale, but just want to get a sketch of it. How do I know it's opening upward? Because it's plus 1x squared. Now, think about this question overall. This question is saying, this statement is saying, where is this parabola less than 0? And the answer is always either going to be outside, to the left and to the right of the two x-intercepts, or in between the two x-intercepts. This is less than. So where is it below 0, below the axis? Well, it's less than 0, starting at negative 1 and going up to 7. In my opinion, it's a lot easier to choose this answer based on my knowledge of what a parabola looks like rather than finding test points and plugging them in. We can talk about test points all day long, but for our purposes, let's try to make it as simple as possible. Find the zeros, think about the shape of the graph, and just use reasoning to figure out where's this thing above or below the axis. Now, if this symbol had been greater than, then our answer would be negative infinity up to negative 1, not including negative 1, and then also 7 to infinity. Or we could have said x is less than negative 1, x is greater than 7. We can talk about the different ways to write this answer. But they all mean the same thing. It's either outside the intercepts or inside. And for this problem, it was inside because it was less than. All right, so probably the most complicated are rational. Kind of like that last one, we want to look for key points like intercepts. But with rationals, you also have the possibility of asymptotes where things can change from plus to minus. So step one on one of these is you need to add fractions. And it needs to be 0. You want to have everything on one side. So step 0 is make it equal 0. And we already have that. So we just need to add these two terms. Now, to add fractions, we need to have fractions. We need to have a common denominator. So let's make this first term stay the same. And our second term, I'm going to make it 3 times x plus 2 over x plus 2 greater than or equal to 0. So I'm not changing the left-hand side here. I'm just adjusting the way it looks. So if I combine these, I'll just, to save a step, this is 3x plus 6, and that's all subtracted. So I get x minus 3x is negative 2x, and I get 12 minus 6, which is 6, over x plus 2, greater than or equal to 0. So this is going to possibly change at either intercepts or vertical asymptotes. Remember, these rational graphs, they have pieces that go like this, and you'll have asymptotes, and then you'll have pieces that look all sorts of funny ways. And the question is, where is this thing greater than 0? Well, that could happen at either one of those transition points, either asymptotes or zeros. So we need to find possibilities. I should have probably left, well, I need to now factor the top of this thing. Let's call the top negative 2 times x minus 3, and the bottom x plus 2. So where's this thing possibly going to change from plus to negative? Well, x equals 3 because of this term. All right, x equals 3 is a 0. This graph goes through the y-axis at 3, and it's either going from above to below or vice versa. And we also have something going on at negative 2, and that's a vertical asymptote. So without having to graph this whole thing, this is what I meant by test points earlier. A test point just means it's a point to the left or the right of to where we know something's happening. Let's imagine a full number line. Something could be going on. A change could be happening at negative 2, and a change can be happening at 3. Now, those are the only possibilities where we could transition from plus to minus, because if, let's say, something else happened at 1, for instance. If something else happened at 1, then 1 would have showed up as either an intercept or an asymptote. It did not, so that's not an option. So a test point is just some number in between, in this range on this number line. So I could test negative 5. I could have tested negative 3. I could have tested negative 88 if I wanted to. Anything less than negative 2. So I need a number between negative 2 and 3. 0 is usually pretty convenient to work with, so let's choose 0. And then 3, anything bigger than that, so I'll take 4. Take those test points and sub them in and see if it's true or not. See if it's greater than or less than 0. So if I put in negative 5, what do I get? I get negative 2 times negative 5 is 10. I'm plugging negative 5 right here. 10 plus 6 over negative 5 plus 2. I don't even really care what this value is. I just care if it's positive or negative. It looks like it's 16 on top and negative 3 on the bottom. And all I care about is that is negative. So the question is, where is this thing positive? Well, it's not positive here because this was a negative value. All right, so that's not a solution. Anything less than negative 2 is not a solution. So what about 0? You plug in 0, you get 6 over 2, or 3, which is greater than 0. So yeah, we've got plus here. So this is going to be part of our answer. And usually these will alternate plus, minus, but not necessarily. So let's check 4. If you plug in 4, you get negative 8 plus 6 over 4 plus 2. That's negative 2 over 6. Yeah, that's negative. So out of my 3 chunks of the number line, where did I get a positive result? Only between negative 2 and 3. And think about it. In order for this to satisfy, we have to be defined there. So is the function greater than 0 at -2. The function doesn't even exist at -2, so we are not going to include -2 in our final answer. That's a round parenthesis because at -2 we have a vertical asymptote, and if the function doesn't exist, it cannot satisfy the equation. So what about at 3? Does 3 work? Because this is greater than or equal to, then 3 actually does work. So we're going to use square brackets. Usually the round parentheses or square brackets will be based on whether or not we have an or equal to, but if it's the vertical asymptote reason for changing plus to minus, then you're going to want to use round because parentheses mean it's not included and it can't be included if it doesn't exist. All right, so that example was probably just as much as all the other ones put together. Those are definitely the tough ones, but follow the same set of steps. Make it 0, add the fractions, find x-intercepts and vertical asymptotes. Let me finish my list real quick. Use checkpoints. And then from those checkpoints, you're determining either it satisfies the inequality or doesn't, and that's how you'll form your final answer.